Hi everyone, in this lesson we are going to go over section 1.4 rational numbers. So in the world of math, we want to describe different types of quantities, and there is a need to use different types of numbers or number systems to describe the things that we want to talk about. So some of the common number systems are listed in this table. They include natural numbers with a symbol of n, and they represent the counting numbers, so 1, 2, 3, and so on and so forth. And then adding to natural numbers is 0, and when we add 0 to the set of natural numbers, we call this number system the whole numbers, because sometimes it is necessary to describe something that is not tangible, that doesn't exist. So it is all the positive integers and zeros. And then of course we know that the number line can show positive and negative values. So when we talk about whole numbers that can be positive or negatives, then we have something called integers. So to show the number system of integers, we're really thinking about starting from the middle is 0, less than 0 or to the left of 0 on the integer number line, we have -1, -2, -3, and dot dot dot, because this range of numbers simply grows to the negative side. To the right of 0, you have +1, 2, 3, and so on and so forth. So both numbers 1 and -1, you can think of them as numbers that are 1 unit away from 0. 2 and -2, these are numbers that are 2 units away from 0, one on the left, one on the right, and so on. Then we have what we call rational numbers. Rational numbers, we use a symbol Q to represent them. And these are any numbers that can be written in the form of A over B, where both A and B are integers. And it's very important to note that the number that you put in the denominator, B in this case, can never be 0. Because when we write rational numbers in this form, this is also saying that the value of these numbers can be found by dividing A by B. So in math, we can never divide by 0 because it doesn't make sense. Therefore, we have to say that B can never be 0. Some examples of rational numbers include 5/4, 3/3. So you may know this, well, this is just 1. Yes, it is. And then you can also have negative rational numbers, because -2 is an integer, 8 is an integer. Sometimes rational numbers are represented using decimals, but numbers like -2.45, 5.3, 2.54, 3.874, 874, 874, so this is a repeating decimal here. These numbers can also be rewritten as what we call a quotient, so a division of 2 integers, A and B. Therefore, these are classified as rational numbers. Well, the opposite of rational numbers are irrational numbers. The symbol is Q with a bar over it. Well, what are irrational numbers? Basically, these are numbers that can never be written in the form of A over B. You cannot represent them using division of 2 integers. Some of these numbers would include square root of 2, so square root of 3, square root of 5. Those are irrational numbers. A non-repeating decimal number like 9.87654321238, blah, blah, blah. This is also an example of an irrational number. Pi is a very famous irrational number. Computers are still trying to work out more digits after the decimals for the value of pi. 2 other famous numbers, some of you may have heard that before, is the golden ratio and also E, the Euler's number. And then we have real numbers. So real numbers are all rational and irrational numbers. So any numbers that you can find on the number line between any 2 integers, those are real numbers. Okay? So after learning about the different number systems, let's do a warm-up. Here's a number line, and which of the following are rational numbers? Place the numbers on the number line below. So first, I've decided to place all the numbers on the number line. So 3.2 negative, 5.89, negative 7, negative 3, and 5/8, 1.9999999, repeating, so it's 1.9 repeating, 2/3, negative 3 and 4/5, 0, and 2.673 repeating. These numbers that we've listed so far are all rational numbers, because any of these numbers can actually be written as a division of two integers. In other words, they can be written like an improper fraction. The only number on this list that cannot be written in that form is pi. So pi is the only irrational number in this list. Okay? And then the easiest way, most of you will think to put these numbers on the number line would be to work out the decimal values of the fractions, like negative 3 and 5/8. How does that compare to negative 3 and 4/5? Well, 5/8 is 0.625 and 4/5 is 0.8. So you can see that negative 3 and 5/8 will be closer to 0 than negative 3 and 4/5. Example 1. Identify the values represented by A, B, C, and D. So in this number line between 0 and 1, so between each whole number, we have divided the section into 4 equal parts. So you can use this property to find the value of A, B, C, and D. So A is 1/2, is halfway from 0 to 1. B is bigger than 1, smaller than 2, and then it lands on the first marking, so this is 1 1/4 or 1.25. If you look at C, it's in the third marker, so this is 3 and 3/4. And D is halfway between 4 and 5, so D is 4.5. So use inequality signs. So hopefully you have seen these symbols before. If not, the one pointing to the left like this is the less than symbol. This is greater than. This is equal to. An equal sign with a line through it means it's not equal. So if we look at A and B on this number line, A is on the left side of B. That makes A less than B. When we compare C and B, C is on the right-hand side of B, so C must be greater than B. And D, when it compares to 4.5, it is exactly at 4.5, so D is equal to 4.5. We will also look at how we can convert rational numbers or mixed fractions into a decimal and quotient of two integers. So when you see a negative mixed fraction, don't be afraid. You can ignore the negative sign for now and treat this fraction as 9 and 4/7. And we learned in earlier classes that 9 and 4/7 technically is 9 whole. Each whole is divided into 7 parts. So when I convert 9/1 into a fraction out of 7, you multiply 9 by 7. So 63 out of 7. And then you add that to 4/7. When we add fractions, you add the numerators. So there are 67 portions of 1/7 of a whole. So putting this all together, we can express negative 9 and 4/7 into negative 6/7 as a quotient of two integers. And then in decimal form, you can use your calculator to divide negative 67 by 7. And that will give you negative 9.5714 and so on. You can round this number into a decimal with 2 decimal places. So when we approximate our answer, make sure we use a dotted equal sign. And this is negative 9.57 because the next digit 1 is less than 5, you round down. Example 3. Convert to quotient of two integers. So negative 0.45, the last digit, the 5, is in 100th place. So you can write this as negative 45 over 100. Both 45 and 100, we can see that these are numbers that end in 5 or 0. They must be divisible by 5. So we simplify this fraction by dividing both numbers by 5 and get negative 9 over 20. You have 2.007, which is in the thousands place. So put 7 over 1,000, 2 is just a whole, and now convert this mixed fraction into an improper fraction. You get 2007 and 1 over 1,000. And then we have some repeating decimals. Is it possible to change them into improper or fractions? Of course you can do that. So the trick here is to let x to represent the positive version of these repeating decimals. We're going to tweak these numbers. The first time we tweak the number, we're going to move this decimal place to the right until it goes behind the repeating part. So in this case, it goes behind the first 2 that you see. When you move the decimal place twice to the right, you're multiplying the number by 100. So you have 100 times x, it becomes 2.22222222. The second time you do this, you want to move the decimal place just before the repeating part. So in this case, the repeating part is 2, so you move this 1 decimal place over as if you are multiplying the number by 10. So you have 10x equal to 0.22222. And now what do? You look vertically, you subtract the two lines. 100x minus 10x is 90x. It's equal to 2. Because all the repeating decimals now have subtracted. So divide both sides of the equation by 90. You get 2 over 90. And that can be reduced by 2 to get 1 over 45. Therefore, negative 0.02 repeating is actually negative 1 over 45. Let's try another example. You have negative 2.464646, so obviously the repeating part is 4 and 6. So we let x to be 2.46464646. So remember the first time, you have to shift the decimal point just to the right of the repeating block. So 4, 6, so just to the right of the first 6. You are multiplying x by 100 here, which means the number becomes 246.46. The second time you do this, you make sure the decimal point is to the left of the repeating part, which is to the left of 4. Well, this is just your original number, so we just write down x is equal to 2.46 repeating. Once again, you subtract the two lines. 100 minus 1 is 99x on the left. 246.46 repeating, subtract 2.46 repeating. This is 244. So x, which is your original number, is now 244 over 99, which makes negative 2.464646 ... equal to negative 244 divided by 99. So this is the end of the lesson. Now go do your homework for section 1.4 as listed on the table.